Welcome back. So there were a couple of calculus aspects that I since added to the memorized sheet. I think they're valuable for here and not just in the lesson. Um, One is position, velocity, and acceleration. So if you're given a function on the praxis and they give you the position with respect to time, you can take the derivative of that and that will give you velocity. If you take the derivative of that, so the second derivative of position with respect to time, then you will get acceleration. And I mean, you could take the integral going backwards as well. Um, yeah, so I wanted to touch on that. You are going to see a position, velocity, and acceleration problem, so it is good to know that that's how that functions. You do a first derivative and then a second derivative, depending on what they're asking you to find. The second piece is critical points and min, max, and inflections. So this actually ties with the position, velocity, and acceleration. The first derivative tells you where the critical points are by subbing in 0 for f prime of x and solving for x. In other words, this is telling you where the slope is 0. Because the instantaneous rate of change is 0 in the original function. So the second derivative then tells you if the critical point is a min, max, or an inflection point. If you sub in the critical point you found in the first derivative in for x in f double prime of x, and if the answer is positive, then it's a minimum. If it's negative, then it's a max. And if it's 0, it's an inflection point, vice versa. It didn't actually create a min or a max point. And that's if it hits 0. So let's take a look at what this is actually going to look like graphically. So here on the left side, I have the function x cubed minus 5x squared plus 2x plus 8. If I take the derivative of that, and I'm going to show it on this one over here, let's see what we would expect to see. We expect to see that the slope is positive over this interval, and right around the axis, the y-axis, it's having a local max. So if we go to our derivative, we should see that too. So it's above the x-axis, so yes, it's a positive slope. And then right here, we see that, oh, yes, there is a critical point. And same spot, 0.214 in our original function, and in our derivative we see that it hits the x-axis at 0.214. So it is calling out a critical point at that spot. And likewise, it should then have the slope being negative between here and here, which it does. It drops below the x-axis, signifying that it is a negative slope. And then we should have another critical point here at 3.12. Let's see if we have it. Whoops, sorry. 3.12. So whenever it hits the x-axis, that is calling out a critical point in our original function, local min or max. And we see that that's true. And we see that the slope was negative, and then it slowly transitioned back and became positive again after the critical point. We see that. Now, if we want to know what actually happened at these critical points for certain, we would then look at the second derivative. So if we do that, I'm going to put our derivative on this screen. So I'm removing it from the screen. I'm going to put the second derivative on the right. So this is the first derivative. This is the second derivative. So if we had these critical points at 0.214 and 3.12, we want to know what happens there. So it looks like when x is 0.214, which is going to be right around there, the output is negative. So that is a max. And then for our second point, that is at 3.12. And 3.12 is going to be positive. So that is going to be a min. Let's see if that's true. So maximum and a minimum for our two critical points. If we go back to our original function, a max and a min, as we expected. So this is what you'll see in graphs, and I wanted to divvy it up a little bit because putting them all in one spot gets kind of convoluted. But that's the idea. You will be probably given graphs on the practice. You're going to have to determine, given the derivative, what's happening with the original function. Or you're going to be asked, is this a possible graph for the original function?